In this section, we are going to talk about uh, alkenes, dienes, and resonance. Dienes are nothing but having two alkene group. So that's why dienes. Di means two. Similarly, for three carbon-carbon double bond or three alkene groups, we'd be calling it triene. And we'd also discuss about what is known as resonance, which is very important in organic chemistry. In this slide, you're looking at a conjugated diene. Conjugated means you have a double bond followed by a single bond, then a double bond. Now, this diene reacts with HBr and it gives a similar reaction with HCl and HI. Basically, the two products that you expect to get, one would follow Markovnikov's rule. You remember Markovnikov's rule? The hydrogen goes to that carbon, in this case, either of these two carbon, carbon 1 or carbon 4. So hydrogen would go to this end and Br would go to the other end. So let's write down in a dotted manner. If hydrogen goes in here, I'm talking about the hydrogen coming from HBr, and Br is getting bonded here. Of course, then there'd be no such double bond. Then you get this product. You get identical product if you apply Markovnikov's rule to carbon 4 and carbon 3. So in that case, carbon 4 would have hydrogen, carbon 3 would get Br, but that's same product as what I have drawn here. If you have a model, you can readily see that. So it's not a new compound. But the interesting thing is, even though this product, which follows Markovnikov's rule, is dominant or major product, you have a small quantity of product which cannot be explained by Markovnikov's rule. So for the second product, this is how the reaction happens. Let me use a different pen color. If hydrogen goes to this end in blue, so if a hydrogen goes to this end, or carbon 1, then Br would go to the extreme end. So this would have Br, and the double bond would move from here to here. Now that puzzled scientists, and they wanted to explain it. In next slide, we're going to show you how we can explain these two types of product formation. One that follows Markovnikov's rule, the other one doesn't follow Markovnikov's rule, rather it's called 1,4 addition, because hydrogen gets bonded to 1 and Br gets bonded to the very end of this series of carbon. Now we can explain it on the basis of a resonance, and we are going to explain to you what resonance is. This shows you the mechanism. This mechanism is very similar to the mechanism of addition of alkene and HBr. We have shown you in the past. So the pi bond that has pair of electrons, so you can think about that there is a pair of electrons in here. Let's use the red ink again. The pair of electrons in here, and that goes to hydrogen, which is delta plus, because Br is more electronegative. So hydrogen is delta plus, Br is delta minus. So when H gets pair of electron from carbon-carbon double bond or pi electron, it cannot hold on to Br because hydrogen can only have one bond or one pair of electron. So what it does, it gets rid of Br. So Br leaves with pair of electrons and Br minus. So this is the Br minus that you're going to see. But what happens is the following. When this carbon is bonded to hydrogen, as you see in here, there's a positive charge development here. And that's carbocation. This is 2-degree carbocation because this positive charged carbon is bonded to one carbon on the right side, another carbon on the left side. And that's why it's a 2-degree carbocation. It's always more stable than 1-degree carbocation. Then Br minus, when gets bonded to this carbocation like this, you get the product which is explained by Markovnikov's rule. But the question is, how do we get the 1,4 addition? Now this has been explained based on the following resonance. After the addition of hydrogen to this end, you have a positive charge here. Now resonance always deals with distribution of charges. If there is a path in which charges can move, then it is going to move, and that is going to provide stability. Now what is the condition here? The atoms would not move, it's only the charge. So let me show you. It may sound like that it can move in any situation, but truly it's not. And I'll show you when it can move. Like in this particular case of carbocation, if you focus on this carbon, that's the carbocation. Now this has unsaturation, has 3 bonds, so it can accept another bond or another pair of electrons. Now that adjacent carbon, I'm going to show you with another color. The adjacent carbon, this carbon, has a pair of electrons here in the pi bond. So what it does, it donates its pair of electrons to in between the 2 carbon, which can accept a pair of electrons or a bond. And that gives 4 bonds to this carbon with red asterisk. So when you do that, you get structure like this. So even though originally I have my positive charge here, after movement of this double bond, positive charge is no longer in that same location. Why? Let's put an asterisk here. Let's count number of shared electrons. Remember, it would only get half of the share. So 1, 2, 3, 4. So there are 4 bonds or 4 pairs of electrons, and carbon would get only half share. So that means it would get share of 4 electrons. And if you look at the periodic table and number of valence electrons on carbon, you find that there are 4 valence electrons, 2s2, 2p2. So carbon is supposed to have 4, and in this sharing, in this molecule, it does have 4. So there is no charge at this center, shown with asterisk, blue asterisk. Now, what about the carbon at the end? Let's count these bonds. 1, 2, 3. So you got the share of 3 electrons, but it's supposed to have 4 electrons because valence electron is 4. It's supposed to have 4, but it has 3. So that clearly tells me that this must have the positive charge. So what's the net result of this resonance? The movement of positive charge from one center to the other center. So what's the consequence of this movement of positive charge? When positive charge is now at this end, Br minus can get bonded at that end. So now you can see that there are 2 possibilities. When positive charge is here, in the Br minus can get bonded there. That gives you 1,2 addition, or Markovnikov's addition. On the other hand, when positive charge is at the end carbon, then Br minus can also get bonded there, giving 1,4 product. So based on resonance, we can explain both 1,2 as well as 1,4 addition product. Now we are going to discuss more about resonance and how it provides movement of all these charges. Sometimes there may not be any positive or negative charge, but there could be simply movement of electrons. Because you all know that charges develop when there is fewer electron than the expected number of electron or valence electron. Now this is benzene. Now you can see that benzene, this is structure 1, left hand side is structure 1, and then this is structure 2. Now how can I go from structure 1 to structure 2? Are they really the same? If you look at the location of the double bond, it's not the same. Because position of the double bonds are not the same. Then how do I go from 1 to 2? This is what I've shown you with the arrow. Now let me show you what happens when this pair comes in here. So when that pair of electron comes in between this carbon, let me write down for simplicity and understanding purposes, carbon. Once you get used to it, you don't have to even write down these. And we need to also fill in with hydrogen. This hydrogen, hydrogen, hydrogen. Here also need hydrogen, hydrogen, hydrogen. Same will be the case with number 2. Okay, there'll be, these are the carbon, and each carbon is bonded to a hydrogen. Now, I'm saying that there is a passage, there is a path for electrons to move in this case. Now, what makes that path? When this electron pair comes here, temporarily, if we can imagine that this double bond remains intact, then let's draw double bond in here, the new double bond. Now this carbon would have too many bonds. If you count it, it has 1, 2, 3, 4, 5. The newly formed second bond makes it 5. We know that it's not possible. Carbon cannot have more than 4. So what that tells us that this bond has to move to this place. That would in turn make too many bonds in between this carbon and this carbon. So that would push this bond to move, this pi bond to move to the next center. So in other words, the movement of one bond really forces the other bonds to move along that ring structure. And that gives rise to this structure. So we now see two very similar structures but not identical. Since I have drawn on that first structure, let me redraw that. Now this time without the hydrogen. I'm hoping that you understood the concept. Double bond, single bond, double bond, single bond, double bond. So that was my number 1. The number 2, we often write down resonance structures with double arrows. Number 2 has position of double bond different. Like in this case, in number 1, there was no double bond in. You can see here there was no double bond in here. But now in 2, we have a double bond in here. Similarly, in structure 1, there is a double bond in here. So basically, I'm just trying to tell you that these two are not identical structures. I mean, I'm talking about in terms of electron distribution. So these are two resonance structures. So actual structure will be given by the combination of these two structures. And we often show it with a circle here. That means electrons move around when you think about these double bonds. So basically it says that electrons can move around the ring structures. In molecular orbital picture, you can better understand this because of the resonance. You can see that these electrons can move around and it would look like this because of the orbitals, that's the combination of all these orbitals. Now, as a result of these, this whole molecule gets stability. Now let me explain to you how that works. In this slide, we are showing you mass distribution and stability of the structures. On the right hand side, mass distribution is not done very well, for which the whole structure is unstable and is falling down or breaking down. On the other hand, on the left hand side, mass is distributed quite well, for which this structure is quite stable. Similarly, resonance through charge distribution provides stability to a molecular structure. So keep that in mind. Whenever there is a possibility of charge movement without moving any atom, then make sure you move those charges, and that gives stability to the whole molecule. Let me go over 48A. This is the question on resonance. So let's go over A. And it's a hexagonal ring with 2 alkene groups. Okay, so here is one of them. The other one is in here, and there's a methyl group here, and the positive charge is here. So this is going to be our resonance structure 1. In order to understand resonance, let's fill in with carbon and hydrogen. At the beginning, this may be helpful, but as you get more experienced, you don't need to worry about writing down the hydrogens. Now here there'd be hydrogen. Now keep in mind that why I'm writing down this hydrogen, because this carbon has 3 bonds. So in order to make it 4 bond, I have 1 hydrogen. Same is the case here. There'll be 1 hydrogen, and there'll be 2 hydrogen at this end. The end which has a positive charge can have only 1 hydrogen. Otherwise, you cannot have 2 hydrogen. I mean, if there are 2 hydrogens, there'll be no positive charge. And you already know how we calculate positive charges. Okay, now whenever there is a passage for the movement of electrons. By passage I mean without exceeding the bond number. Like in case of carbon, the bond number is 4. So without violating that, we can move electron pair or charge from one atom to the other atom without also removing any atom. So in this particular case, the double bond can move to the next carbon-carbon bond because those carbon-carbon can accept 1 additional electron pair because they have only 3 pairs of electron or 3 bonds. So it can go over there. So that there is no restriction in this passage. So what would it give you? Let's draw that. Again, I'm drawing 6-membered ring, this time without the hydrogen, or only the minimum number of hydrogens so that it doesn't look messy. So I'm going to write down hydrogen here. My double bond is in new position. This is the new position for the double bond. And this is my old double bond that remained in its own place. Now the question is, let's find out which one lost its second bond or double bond. You'd quickly find out that this is the carbon that lost its second bond as we moved it from that location. So loss of bond means there will be charge development, because original charge was here. After this movement of electron pair, the charge is now in here. You can always double check that by counting shared electron, which would be 3 because there are 3 bonds, and carbon is supposed to have 4 electrons because there are 4 valence electrons. Supposed to have 4, but it has 3. That means it's positive 1. So this is also a valid resonance structure, so structure number 2. Now, can we draw any other structure? Answer is yes, because you can see there is an electron pair here, the double bond. It can provide electron to that carbon, or it can go in between these two. And that's what's going to happen here. Double bond now comes over here. Without violating any rule or bond number, electron pair can go over there. Because now those carbon would have 4 bonds, so it doesn't go against any of these established rule. So let's move it and see what we get. So now you have a double bond in here. This is CH3 group, and we have a new location of the double bond. Now we can quickly find out the positive charge by knowing the carbon that has lost its double bond. It is this carbon, and so that carbon would have positive. In order to count a formal charge, make sure you know that there is a hydrogen bonded here. So what we see here is the positive charge moves around from this location in structure 1 to this location in structure 2 and this location in structure 3. So these are the two additional resonance structures for this particular molecule or ion. So altogether there are 3 resonance structures, but they have already given you one. Let's try now another compound, which is 48C. For 48C, let's use again a different pen color. Let's draw a line here. 48C, again I have a 6-membered ring, so let's have a 6-membered ring. So that's 6-membered ring with electron pair. This time I don't have a negative charge, I don't have a positive charge, but I have a negative charge here. This is the double bond O. On this end, I also have a double bond O. Okay. Now the question is, how many resonance structures are possible? If I call this structure number 1, can we figure out any passage of electron? Yes, I can. Electron is in here, negative charge. Electron can come over here, even though that carbon, this carbon has 4 bonds. Electron pair can still come over here, because when this carbon sees too many bonds, it's going to get rid of its pi bond. So in other words, without moving any atom, I can still move my electron pair, and that's a good passage for the movement of electron or negative charge. So what's the end result of this? Let me just show you on the top. As a result of this, okay, I now have a double bond in here. Now this double bonded oxygen is remain intact. I now have a double bond here. Remember I mentioned that oxygen has to break its double bond, would have now a single bond, and rest are electrons. Now that gives 2, 4, 6, 7, because 1 is coming from the shared electron pair. Neutral oxygen is supposed to have 6 valence electrons. Now this has 7, so it has to get minus. I'm going to write down -1 here. So -1 or minus, both are the same thing. So that's my resonance structure number 2. Can I draw any other resonance structure? Yes. Instead of electron pair going to the right, it can go to the left. And that's what we're going to show you next. Electron pair from structure 1 can go to the left here. Again, now this carbon would have too many bonds because it already had 4 bonds. So it has to give up its weakest bond. Whenever there's a pi bond, it can release those electrons onto oxygen. So in other words, this kind of movement of electron is quite possible. So let me show you that structure. 1, 2, 3, 4, 5, 6. Okay, now this time this is going to remain intact. Now double bond goes in here. Now O is now in here. 2, 4, 6, 7. So that makes it minus. Minus is same as -1. So that's -1. So this is going to be our structure number 3. So you should understand that how these structures are drawn. Keep that in mind in moving these charges around or electrons around. I haven't moved any atom, and you're not allowed to move any atom. So only thing I have done is I moved electron pair from one center to another center or in between two carbon and broke the weak pi bond, and which is quite allowed.